an honor and a privilege to be here with you all. So I just took pictures of the audience with so many friends and familiar faces, which is great. So I love the title of the conference, The Many Legacies of Richard B. Stanley, Immense Might and Glory of the Epic Babylonian Rascal. It just seems so appropriate. So I'm looking around my collection for pictures of me and Richard because I spent a lot of time with Richard over the years, and he's just a super wonderful person. I really enjoy all the time we spent together, but honestly, the last picture together might have been this one. Somehow I left MIT before the time where we walked around with a camera in our phone in our pocket all the time, so I have very good pictures. But well, you probably will recognize him, he's there. And some of the other people in the audience, you can see we're practically together. Anyway, that's a picture. So thank you. That was from about 30 years ago. And I was going to say thanks for all the math over the last 30 years, but I guess actually it's probably a little bit more like 50-something years. So I put 52 up there, and then I think, well, maybe actually it's been doing this since birth. So, so then I typed in 30, 50, 280 into the apps to see what you get. It's a really nice sequence, actually. I didn't know. It's the twice second pentagonal numbers.
Is it in the encyclopedia of vintage?
Yes, of course. The next number, does everybody know? 114. So that's, I guess, we'll celebrate that one too. Okay, so I want to talk to you a little bit about the background on Fubini words and some varieties introduced by Pawlowski and Rhodes. And what we've been looking at lately, this is based on joint work, I should have said, based on joint work with Matthias Kombolinka and Stark Ryden. We've been looking at partial orders that are related to these varieties, natural analogs of Bruhat order. And we have some results in terms of like generalized Erzman criteria and Bolton's essential set. And I wanted to kind of merge some of things that we've been doing with a recent visit. Matthias came to visit in March, and we had a really wonderful, productive month. And I started talking, he gave a talk on alternating sign matrices, so that was the natural thing to merge, I guess. We ended up with quilts of alternating sign matrices. I'll tell you what that means. And if I have time, I'll talk about it. Okay, so the story starts with this work of Pawlowski and Rhodes, and they were studying a geometrical object, which is very natural. I'm surprised that this wasn't already better studied. So they're just looking at the space of all spanning line configurations in, let's say, complex k-dimensional space. So since they're lines, you can think of them as like some tools going through some point, which is the origin. And since they're spanning, there's going to be enough of them to at least have a basis, but probably more. So the picture might look like a pincushion thing like that. And if I was going to hand you a spanning line cushion, I could hand you the zone tool, or higher dimensional, that's going to be hard. So I would probably hand you a matrix, right? And matrix would be a K by N matrix. Each column represents one of the lines. They're ordered. These spanning line configurations are ordered, so that the order of the columns matters. And I could rescale any of the columns, and it would be the same spanning line configuration. So there's some redundancy in this representation, but that's the way I can convey it. So I probably would rescale as one of the entries to be 1. So let's use some notation then. So for the we have to have full rank matrices because they are spanning line configurations. So let's let F and K be the full rank K by N matrices, and we'll have no zero columns because each of those lines has to be non-degenerate. No zero columns at all. B is the upper triangular matrices as usual, and T will use to report the diagonal matrices on the right-hand side of the G, L, and diagonal matrices. And the thing that Pawlowski and Rhodes were studying is this collection of all of the spanning line configurations. So we'll call that X and K, and it's a smooth, complex projective manifold. It sits inside of this projective space, this manifold. So you take the spanning line configurations, and it's easy to just embed that into the projected K-1 dimensional space and calculate just each of the lines. Okay, and you can also think of it as a quotient of these full rank K by N matrices modded out by the T action on the right, those orbits. So easy examples, what if you have A equals 1? So 1 by N matrices. The entries would have to all be non-zero because every column has to be non-zero. You could rescale every column so something is 1, so you just have 1, 1, 1, 1, 1. So that's an easy one, that's a 1-point space. And the spanning line configurations X and N. Those correspond to the invertible matrices modeled on the right by diagonal action. So that space has a nice projection onto GLN1B, which is an old friend. That's the analog of the flag manifold for type A. And this is a homotopy equivalence. They actually have the same cohomology in that case. Okay, so why were Kowalski and Rhodes looking at these? They've actually been motivated by a ring that generalizes the covariant algebra that Hagman, Rhodes, and Shimizuno had introduced a couple of years before. And they were looking for a geometric interpretation of this ring. So the normal covariant algebra is polynomials and n variables and mod out by the elementary symmetric functions. And so the generalization here is you still have polynomials and n variables, you mod out by the trailing elementaries and also the k powers of all of the variables. So you get a ring indexed by n and k. And this has a natural SN action on it again, just commuting the variables. And there's also an SN action on the n tuples of line configurations. It turns out that the SN action there's a corresponding action on the cohomology ring, and it ends up the cohomology ring of spanning line configurations is isomorphic to R and K, even as an SN representation. So that's really quite a nice result. They have a lot of wonderful geometry in the paper. I highly recommend. And one of the key ingredients in their paper is the cell decomposition of the spanning line configurations. So they're doing this in a fairly natural way. You can use Gauss elimination type methods again. So if you think about the lower triangular matrices acting on the left, and they would do row reduction. So we'll take any k by n matrix that's full rank, no zero columns, and then it has to have something non-zero in the first row. So when looking for the first entry, rescale it to be 1 and use it to clear out everything below. And then do it for the second row, and so on. So when you do this, you're going to have these pivot ones that are going to form a permutation matrix. But you'll have some other columns that have some non-zero things, right, in other places. So the data that we're going to attach to such a matrix is, first of all, where are those pivot ones? So the pivot one in the first row is in column 2, so that would be alpha 1. The pivot row in the second row is in column 4, so that'll be alpha 2. That's fine. You get this whole alpha vector. And we also have the permutation matrix that's underlying that, right? So that's the permutation matrix for 4, 1, 2, 5, 3, doing it by columns. All right, and now I want to associate to this matrix, and every matrix is going to get associated to some word. How do you do that with this data? Well, in each of the columns, at the beginning it's easy. So for the first column, associate that to the letter 4. And the second column, associate that to the letter 1. What should we associate to this column that doesn't have an initial one, it doesn't have a middle one? Well, the way that you're going to do that is start from the back of this permutation. Does it have a 0 in position 3? Yes. Keep going. Does it have a 0 in position 5? Yes. Keep going. Does it have a 0 in position 2? Yes. Keep going. Does it have a 0 in position 1? Well, not. If this was not 0, we would stop. And we would make the third letter in the word be 1. And just keep going from that. So to every matrix, they get grouped up, first of all, into orbits under this lower triangular action, and second of all, according to this word.
Questions. Sorry. About the question about the previous slide. How do you define this space? You define this as a subspace of the projects?
Yes, yes, it has some embedding.
Right, projects. Exactly, the specification of its itself project.
But the space is not compact.
So then we talk about homology to couple. So then we talk about homology to define inside of the projects.
So they did have to think about how it sits inside the matrix. Yes. Yeah. It's a bit of a tricky business since okay, so we have this way of partitioning all of the k by n matrices, full rank, no zero columns, into classes corresponding to words. These words are always going to be on the letters from 1 to k, and they will be length n, right? So, and with each of those words, we're gonna associate to it a special matrix, they call it a pattern matrix. And this is basically the generic form for all the matrices that sort of end up under the lower triangular action, reducing to this one. So there's just a little bit extra that's going on here. So when we have redundant letters, we're gonna find that non-zero thing in the particular column, so that like column 2, row 2, sorry, column 3, row 2, we're gonna rescale that entry in particular to E1. So this is gonna tell you exactly which of the non-zero entries, one in each column, then a rescale to E1. Some of the entries will be stars, and that's because it's cell decomposition could be any complex number there. And so, for example, this matrix, which represents some spanning line configuration, k equals 3, n equals 8, corresponds to I have the pattern matrix in my mind as two things at the same time. It is this picture with zeros and ones and stars, and it's also a collection of sets where you take stars replaced by it. That matrix would be in this. All right, and so what's special about these words? Anybody see anything special? This is not just an arbitrary word in the alphabet 1 through K, right? Because of this full rank business, you know that you're going to have the numbers from 1 to K will appear in there at least once. They have to all appear. And these kind of words seem to come up many times in the literature and not really under a unified name. So Hadowski Rhodes, I think, following Andy Wilson, they call them Fubini words, but I also have heard now Cayley words, preferential arrangements, rejected words, packed words. Coupon collector words, yes. I just say, oh, maybe the right figure out the name, yes.
For the matrix, how do you decide the zero?
Oh, so if you hand me a spanning line configuration, then it will just automatically have some zeros in it, or none. If it has none, then that's okay. But after you do that row reduction process, there will definitely be some zeros. And that's what's going to determine the pattern matrix. Okay, so there's lots of words for these things. I like the word Fubini because they are counted by the Fubini numbers. And this is an early sequence. The LAIS is just number 670, so it seems like reasonable precedent. So let me use WNK for the set of all Fubini words, specifically of length n on the alphabet from 1 to K. So we have this one in W83. And of course, a Fubini word, then you can also think of it as an ordered set partition. It's basically the same thing, which may be more familiar, but this is the Fubini words are going to represent surjective maps from the numbers from 1 to n, 1 to K. So you take the inverse image of 1, the inverse image of 2, and so on. You sort of get an ordered set partition. So in particular, WNK that is counted by K vector times the starting numbers of the setting. And a lot of the properties of permutations carry over to the Fubini words. The N Fubini words, of course, which is permutations themselves. And you can do things like look at descents or inversions and lots of nice things and get statistics. Or you could do something like take the analog of the permutation matrix. And the permutation matrix is going to be in the particular pattern matrix for the same word. Okay, so back to the Pawlowski-Rhodes picture. And if we let U, K be the lower triangular matrices that all have ones on the diagonal, and each of the spanning line configurations for X and K can always be represented uniquely as a product, something lower triangular like that, from something in one of these pattern matrices. That's the cell decomposition. And each of these cells, UK, PW, it's easy to see what their dimension is. It's going to be K choose 2 because of the UK part, plus the number of stars in the pattern matrix. It's got nice contours. And so these cells, let's call them C sub W for a particular word W. We're going to call those the PR cells. And if you take the closure inside the spanning line configuration, that's the PR varieties. And these cells are certainly determined by certain spans and things that you can write down in the rank conditions. And we're interested in seeing how this geometry kind of works together. So a natural thing to think about is which of the Pulaski Rhodes varieties are contained in which other ones. That generalizes the idea that comes up with super varieties very nicely. So we can define what Stark-Dragon and I call the medium roast Fubini-Bruhat order. That's the first variation in the theme. To be the poset where a Fubini word V is less than W, if and only if the reverse contains false. Pulaski Rhodes varieties V contains CW. Natural enough poset to study, right? Generalizes Bruhat order. It respects the codimension, so increases as you go up. It's not a ranked poset, so that was kind of a surprise to all involved, but makes it a little hard, but that's not so bad. But the next line is kind of a little bit trickier. So the next statement is that when you look at these varieties, they don't line up quite nicely. They can be the case of the closure of one can intersect another cell but not contain all of it. So they kind of stack that group. So here's the picture I kind of think of as poorly stacked cubes when you look at these closures. Yeah,
Well, what's the definition of espresso?
it's coming, yeah,
Oh, espresso.
coming from this, right here. So since we have something not quite as nice as with super varieties, we do have the case that sometimes a Pulaski Rhodes variety can touch another cell but not contain it. So let's add that as a definition. So V touches W near some intersection. So that includes the case completely, but it also contains more. So that's if we add all of these extra relations and then keep the transfer closures. That's the espresso Fubini. So it's a little bit stronger. Okay. And then there could be the decaf version. There's a couple of naturally covering relations, but Pulaski and Rhodes have left it as no problem to find the covering relations in this poset. They're actually quite hard to describe, and it's still an unsolved problem. But some of the covering relations that are easy is just like regular Bruhat order has covering relations in terms of transpositions. Those also occur here. Another simple one is what we could make to call pushback, and this is just sometimes you could take a 1 and move it to another spot, introducing exactly one other star in one column like that. And that's going to absolutely definitely be a covering relation. This poset decreases the dimension, codimension by 1. Both of these do. And so the decaf order is just Bruhat order in SK crossed with this pushback operation, where you do it always on Fubini words that have initial permutations of the idea. So this is just the product of two ranked posets. So you get a ranked poset, it's nice. And it's sitting there inside the medium roast, which is sitting inside the decaf, or inside the espresso order. And this partial order is nice, and it does have this Q analog of Stirling numbers, K factorial Q by as its rate generating function, and that's also the form of real polynomial for long-term for the spectrum line configurations. Okay, so here's a picture of this, all three orders trying to draw them on one picture, one Hasse diagram. I don't know if there's a name for a Hasse diagram, 3 kinds of posets, but so the thinner edges are the decaf, you add the red edges, you get the medium roast, you add the red and blue edges, you get the espresso roast. Okay, so I wanted to say what we've done here a little bit, and the theme is that we've tried to make it a little bit easier to figure out the relations on these elements, the Fubini words from a combinatorial point of view. And in order to do that, we had to sort of be a little bit more clear about what are the equations defining these varieties. So let me just say a little bit about the notation. So n choose h. If you put square brackets around the n, that would mean all the subsets inside of h. And I don't know if you've done this before, but I put square brackets around the bottom two here. So this means all the subsets of 1 through n of sizes 1 through up to k. And okay, so we use that now to describe some of the special minors on these matrices. So in general, just delta ij is the usual group coordinate site. Take the rows from I, the column from j, and take the minor corresponding to that. But the flag minors are the ones indexed by just a subset of columns. And if you take just a subset of columns, the thing to do is to take the first so many rows that match up whatever the size of j is. And those are the flag minors. They also play a nice role in the cluster outro. So these flag miners seem to be the critical piece in the story for us. So why are the flag miners important? Well, because if you have one of these pattern matrices and you multiply it by lower triangular matrices, you won't be changing whether or not one of the flag miners vanish. You might be changing whether one of the arbitrary miners vanish, but not the flag miners. So they're more stable. Okay, so, and given any one of our Fubini words, we could figure out which of the flag miners vanish all the time, or some of the time, or none of the time, on that whole Alaskan road cell. So SW for some of the time, T for truly, which means all of the time, and U for unvanishing, never. And these sets play an important role. So in this case, let's see, what are the truly vanishing miners? Well, certainly this top entry, even if you were to multiply by a lower triangular matrix, that top entry would certainly still be 0. And also like this 2 by 2 miner right here, that one would also be vanishing on the whole cell. So 1 is in this set of truly vanishing non-nuclear miners, and 1, 2, and so on. Those are just the column sets that you need. But for every Fubini word, you can figure out what are the truly vanishing miners. And so the Pawlowski Rhodes variety C sub W, the closure there, is exactly the vanishing set that goes with the truly vanishing miners and nothing more. Like you don't need any other things to describe. You don't need all of the miners, you just need these flag miners. And so the corollary of that is that the medium roast is easy to figure out that V is less or equal to W if only the truly vanishings for V are contained in the truly vanishings for W. And the espresso roast is also pretty easy. This is the case that the truly vanishings are contained in the sometimes or truly for W.
Sir?
Yeah.
You say vanishing set is the ideal generated by the
No.
W's? Okay.
Right, it's a different ideal. Which kind of surprises, but of course, just think about it. This entry here vanishes all the time, right? Vanishes, actually doesn't vanish all the time. Let me see if I can point to a better one. I'll apply my eye.
I don't think that was my question.
Ah.
Is the ideal generated by the W's radical?
No, so no, it's not the same as all of the miners that always vanish on the cell. But it does carve it out inside F and K, the set of all full rank matrices with no zero columns. That's what you need to have just on that stuff. So it is a little bit different. Okay, so we wanted to get something like the Arrowsmith criteria for Bruhat order. I don't know if you've seen that before, but it depends on the scale order. Actually, a Gale order is a little bit of a misnomer, but Warren and Federico and Felipe had used this. So I decided I've always needed a word for this. So I'm going to So this is when you have 2 sets and you want to compare them, sort them into increasing order, and then compare entry by entry. And so this was the order used by Arrowsmith long before Gale, but we'll stick with this. And another piece of data that you're going to need to know is we had the alpha vector for W. This is where those initial columns. And let's expand that to the alpha vector for any subset J. And we'll just take alpha sub whatever W of J is. And this will be a multi-set. So for example, well, in this word, alpha of W was 2, 4, 6, 1, 5. And alpha of the set 1, 2, 3, 8 would be pick out columns 1, 2, 3, and 8 and write down the corresponding subscripts. So alpha 4, alpha 1, alpha 3, and then figure out what they are. Okay, so here's a theorem with start drawing, and that is if you want to compare, if you want to know if a particular flag miner is sometimes vanishing or truly vanishing or unvanishing, you just do the Gale order with the original alpha vector up through H is the size of J, and compare that to this alpha J vector, the Gale order. So it's pretty easy to do. And this means that then we can get a nice way to describe when is V less or equal to W in the medium roast order? Well, you just have to compare every time you have the set alpha 1 through alpha H of W is less than alpha J. We also have to have the same thing for the V. That follows. And you can do something with this espresso roast as well, because we can also characterize the sometimes vanishing minors. So that works out to be fairly easy and a nice generalization of the Ariston criteria. And then I'm kind of flipping through that a little bit fast because I see I'm getting low on time, and I did want to say how we're brewing this up with the alternating sign matrices quickly. So on the left, we have an alternating sign matrix. That means it's a matrix of zeros, ones, minus ones. And the property, as you read from left to right, it starts with a 1 and then it alternates minus 1, 1, minus 1. So the permutation matrices are in there. And so are those Fubini-Bruhat matrices. If you go up from the bottom, you also start with 1. But when you have a k less than n situation, it may not be true that it's reading down from the top, that you have to always start with a 1. But these, let's say you always have 1 as you read up and from the left, and you can create a cornerstone matrix that goes with it. This was already in Bill's from Steve's paper. This you just sum everything from every position, and you look down and left and sum all the numbers that you see there. You get the cornerstone matrix. And of course, from here you can go back. But next to you take. You want to know what entry this corresponds to, you take this value minus its neighbors, and then add back to the triangle. Okay, so these are basically the same object. Alternating sign matrices, column sign matrices. Okay, so a theorem of Lascaux and Chitzer-Berger from '96 is that the dedicated completion of a Bruhat order is exactly the same as the partial order given on these alternating sign matrices, and the partial order is by comparing their cornerstone matrices entry by entry. And so it would be curious if we could generalize that, because we'd like to understand these, at least the medium roast Fubini orders better. And we also have these rank functions sitting around. So we were comparing that with the cornerstone matrix. Well, what happens in a cornerstone matrix? Well, this is like a function, it's a matrix, right? But you can think of a matrix as a function from the chain poset to the chain, across the chain poset to natural numbers. It's padded with zeros along the left and along the bottom. So we'll have zeros as a basic condition, and then at the top they actually achieve whether the minimum is in k and n. And as you step right or up, you either have equality or you go up by exactly 1 and nothing else can happen. Right, so they kind of have this monotone growth property. And the same thing happens on the rank functions for these Pawlowski roast varieties. That you can think of them now as functions from the chain CK cross Bn, so they're natural numbers. They have the base case at the bottom. They have to achieve a certain level at the top, and the steps always are either going to be the same or one more. And this is just for any matrix, right? The rank, you add one more column to the rank, one more column to the matrix, its rank goes up by 1 or stays the same across the bottom. So we have the easy characterization of this medium roast order. CV is less than CW if and only if the corresponding maximum rank functions FB is dominated by FW.5. Okay, and so you can interpret that then, since these max rank functions look a lot like cornerstone matrices, there is something like an alternating sign matrix that goes with this as well. And we can generally, we started thinking, okay, well, you can do this for CK cross CN, you can do it for CK cross BN. You could actually also look at the data for any matrix, take any subset of rows and any subset of columns and ask what is the rank. Gives you another function on BK cross BN. And why stop there? So let's let P and Q be any two finite rank posets with a 0 and a 1. And then we'll call this thing a quilt of type PQ. If it's a function from P cross Q to the natural numbers, it has the base case, it's always 0 if either one of the indices is the minimal element. Once you get to the F of the maximal 2 element, it's going to be the minimum of the rank of P versus the rank of Q. And every time you have a covering relation in the product poset, this value of the function has to either be the same on both or step up by 1. Okay, so that's a reasonable generalization of the more like a generalization of the columns and matrices, but sitting inside there is a related alternating sign matrix. And in fact, you can think of it as, the reason we named it quilts is because anytime you take a saturated chain in P and a saturated chain in Q, you could get back to a Borderson matrix, and so you could get back to an alternating sign matrix as well. And so here's an example of a quilt for B3 cross C2. And for each of the saturated chains, the corresponding alternating sign matrices. And they kind of weave together in some consistent ways, and hence the quilt. So this is now the work with Montes Kovalinka, and we have some nice things to say about it. You can get a poset on the quilt easily just by comparing entry by entry. If you look at it though, it's easily seen to be a distributed lattice. The meet and join are just min and max. It's ranked by a nice function, basically in terms of just summing the entries. And so now we have this nice distributed lattice, and actually what we're trying to get to with the medium rows is what are the covering relations? And at least in this poset, this quilt lattice, it's really easy to pick out one of the atoms in any interval between N and G. And that's in terms of a graph on the differences. So there is a directed graph that we can find exactly index the atoms. So here's what it looks like for just V3 cross C2 is a lot of data. And inside there are the alternating sign matrices and also some of these medium rows from medium words, which are sparsely populated. So this is not the last equation, it's too big. But it still seems to contain it in a nice way, both in capitalism. Now, at first we were hoping we could really enumerate some of them, but it's not hard to see that it's actually sharply complete to enumerate an arbitrary number of quilts for an arbitrary P and Q. So that's out of the question. The reason this is true is it relates to the Dedekind numbers, which are well known hard. The Dedekind numbers count the number of antigenes in the Boolean lattice, and they're not known for B10. And okay, so it turns out that while we can't do it in general, if you look at special cases, we were able to get some nice results. So let me just give you two of them quickly. I'll quit. And so if you have a poset, which is basically an anti-chain, but you've attached a 0 or 1 to it, then you can get a nice formula in terms of sum over all of the convex cut sets of P minus the top and bottom, and then count the number of anti-chains in there, which is hard. So you can sum it up like this. And maybe the more efficient one is what happens when you take one of the posets to be a chain, in which case, chapter 4, at least one comes up, and the transfer matrix method helps you to see the generating function right off the bat. And since the denominator is that nice 1 minus x to a power, it's a polynomial in terms of n. And so that's the enumerated results. Leaves open a bunch of open problems. We're still looking for a nice description of the covering relations for the espresso and the medium roast from medium orders. And what other properties of Bruhat order generalize? And now this is our most recent question, papers coming soon, hopefully. What are the other properties of the alternating sign matrices and the corner sign matrices that generalize to the close? What could we do with these much richer structures?